Okay, so and I forgot to turn the screen on. Okay, but we are any second now. There we go. Okay, so so last time we were talking about, I forgot my mask. We're talking about different ways to represent functions with pictures, right? And again, in high school, in single variable calculus classes, practically always that we represent functions with a very specifically constructed kind of a picture called a graph. It just doesn't seem like it's a choice because it's the choice we always take. It almost seems like a requirement, right? But very importantly, it's not. It's just one way to represent a function with a picture. And we've now seen various other ways to represent functions with pictures. So be careful. Don't confuse them. So if you're relating pictures in algebra, you need to be very clear in your mind, and ideally as clear as possible to the reader. What is the nature of the relationship between these things? So here's an example of the kind of confusion that can come up if you're not careful about this. So here's a line. Right, here's the equation of the line. So what function are we looking at here? I ask rhetorically. And it's tempting to say, well, it's a picture, therefore it's a function. So, what function is it? Well, the moral of the story here is it really depends, again, on what kind of a relationship between geometry and algebra are you talking about. So, in particular, this line that we've got here, this is a graph of one function. It's a level set of a different function. And it is parameterized by yet another function. So, what function are we looking at here? Well, depending on how you want to think about pictures, it could be any of these functions. Be clear, be careful, right? You don't want to take an idea, like a tool of calculus, such as what we're going to be seeing coming up very soon here, hopefully today, even getting started, and take calculus ideas that were intended to be applied to graphs of functions, and apply that instead to a function whose level set is what you're interested in. Right? This is the wrong function. This is the function you need to apply it to. Okay. So now let's walk through. First, I got a little ahead of myself. I say that this is a graph. What function is this a graph of? And let's keep in mind what graph means. When you take a graph of some function, you're going to take the value of the function and you're going to set it equal to a new variable. In this case, y, right? And then this, by virtue of setting the function equal to y, this becomes the graph. And now you can see a function that I've chosen here. If you take this function f, you set it equal to y, thus again, taking the graph of that function, you'll note that it's equivalent to the equation of the line. You can kind of move things around there, multiply the 3, shift terms around and such. And that is that line. So this line is the graph of this function. All right, now that doesn't directly answer the question, though, of where did I get the function in the first place, right? What I've done here is confirm that its graph is the line. But if this were, if more of a question of, what is the function whose graph is this line, right? Then again, how do you get it? And you basically just reverse engineer this process. You say, well, I'm going to need to set something equal to y, so maybe I'd better solve for y in the equation that I want, and then setting that thing equal to y is just really going to give me exactly what I had before. So the way you find the function whose graph is that line is just by solving for y. Okay. All right. Now, next thing, I claim that this is a level set. This same exact line that we just got through realizing as a graph, it's also a level set. It's a level set of a totally different function. Keep in mind how level sets work. A level set means that you're going to take your function and not set it equal to a new variable. You're going to set it equal to a constant. And so this function set equal to an appropriately chosen constant gives that equation. Now the algebraic manipulations on this one are 0. Right? You don't have to solve for anything or move anything around. This equation, as it happens, conveniently in this case, happened to be given to us as stuff equals constant, and so it was very easy to make this happen. Not hard at all to see how how to find this function that when I get set it equal to a constant gives me stuff equal to a constant. I guess it's already done. Right? So that was a relatively easy one. But notice now in particular, these two functions are different. Right? The function whose level set is the curve. The function whose graph is the curve. Same curve, different functions. Is everybody happy? Everybody see what I'm talking about? Okay. All right. So again, we're going to eventually have what I'm going to call a calculus of graphs. We're going to understand relationships between derivatives of functions like this and geometric interpretations on the graph. And it's going to be useful stuff, right? But very importantly, the calculus of graphs applies only if the picture you're looking at is the graph of the function you're doing to the calculus to, right? So you got to make sure of the connection. We will also have a calculus of level sets. There's going to be certain calculus things that you can do to a function that will tell you about, that will relate geometrically to its level sets. Again, you got to make sure you're using the right function. You don't want to apply the calculus of level sets to that function, and you don't want to apply the calculus of graphs to that function. Okay. All right. Last observation, real quick. I'll point out that this is also parameterized by this function right here. It's not too hard to see that this point, for example, is 0, 2, which you see right there, and then this direction vector. Not too hard to see, is 3, -2. And so what we got here is basically A plus TV for that point, purple point A, and that green vector V. So this is a parameterization of this line. So now we have actually 3 different functions, right? 3 different functions. And in the same way that there is a calculus of graphs and there's a calculus of level sets, there is a calculus of parameterizations. They're all the different calculuses are different. And so again, don't apply the calculus of graphs to this function. Doesn't make any sense. Okay. All right. Everybody good? Okay. All right. And I've already walked through this. Just to be, I guess, a little bit more explicit, tempting to say the derivative of a function gives you the slope of the picture. Oversimplification. Derivatives of functions gives you slopes of the graph of the function. So notice we are not looking at a graph of g. And so taking derivatives does not give us the slope of the picture because we're not looking at the graph. We're looking at a level set, and that's totally different. Okay. Here's a neat observation. This is a good little trick, a little tool for your toolbox. It centers on this algebra right here. Notice this algebra is extremely not tricky. Right? This is hardly anything happened here. I took sort of all the stuff that was on the right and I just kind of subtracted it over to the left. Barely anything happened. But there's an important interpretation of what we did here. Because in the top line, notice we're looking at, it's written anyway as a graph. This is written as a graph of, let's see here, of this function there. It has n input variables, 1 output value. So it's from Rn to R1. And this top equation is looking at the graph specifically, right? Setting it equal to a new variable. All right, but then the thing is, this algebra down here, we're looking at a level set. You can see it's a level set because we have equals a constant. And, constant happens to be 0. It's not required, but whatever. We have stuff equals a constant. So this last equation is written as a level set. Specifically, a level set of this function here, which you'll notice is not a function of n variables. If I want to say this is a function I'm setting equal to a constant, it's the whole thing on the left that is that function. And there are n plus 1 variables because there's the n x variables, and there's also a y, also a variable. That's part of what's on the left-hand side. So, so what's nice about this, again, I'll remind you that you have to be careful about the difference between graphs and level sets. And what is a graph of one function is a level set of a different function. This process, though, shows you how to, anytime you have a graph, right, any graph at all, you can always do this move. You can always take what's on the right, throw it over to the left, and have a constant, therefore, remaining on the right. Always doable. And therefore, we get to conclude that whenever you have a graph, you can always view it as being a level set of a different function. Why do we care? Well, sometimes we're going to find ourselves looking at a graph. That's just what we're interested in for whatever reason. And the thing that we need to analyze on that graph, though, oh man, the calculus of level sets sure would be handy. Right? The calculus of level sets gives us different geometry. And it'd be nice on many occasions that we will see that we're looking at a graph, but man, those tools in the toolbox for the calculus of level sets, I wish I could dip into those because that would give me exactly what I need. Here's what you do. You take the function whose graph you're looking at, you do this one little move, and then you get to say, oh, cool, look here, check it out, here's my new g function. I am, in fact, interested in, the graph that I'm interested in is a level set of that function. And go ahead and knock yourself out, use all the calculus of level sets that you want on this function. And that will allow you to make geometric interpretations of this graph that you were given initially. Yeah.
So that graph and that level set will look the same, right?
That's right. That's why I have them in a box in purple. These are literally equivalent equations. That's right. And so their pictures, the surfaces described by these two equations are identical. That's right. Exactly. All right. So it's a good move. Here's an example. Here I've got a graph. Specifically, we're looking at the graph of this function, x squared plus y squared. And yeah, it's a graph. That's nice. The calculus of graphs will tell me some things. But if I needed the calculus of level, again, I can't tell you what's in the calculus of graphs, calculus of level sets just yet, where we need to develop those ideas, and that'll take us a little time. But there are some things that you can do with level sets that are really handy. And if you wanted to use one of those level set tools, just do this one little bit of algebra. Again, the algebraic trickery there is practically nothing. Just move all the terms over to one side and have equals 0. Choose your constant, it doesn't matter, on the right. And now, sure enough, we're looking at a level set now. This is a level set, and it's a level set of that function. So apply your calculus of level sets to this function, and you get to draw conclusions about your graph you had in the first place. Bad news, this is a one-way deal. Not every level set is a graph. It just doesn't work out if you just try to reverse the algebra around. Easy counterexample. You look at this. Well, let me try to keep my colors consistent. This equation here. This is a level set. Right? It's a circle. And it's just not a graph. Try as you might, you can't solve for x and you can't solve for y. And by solve, in this case, I mean do the algebra needed to find a unique value of one of the variables that satisfies the equation corresponding to the values of the other variable. So that's the uniqueness that's the problem. Yeah, of course, there's two possible values of y. Sure, yes. But in the sense that we're talking about solving here, in the very precise sense of finding a single value that works, you cannot solve for x or y. Okay. So, again, one-way trick, unfortunately. All right. Here's a neat little fact of multivariable equations. If you're looking at a rectangular equation, and if x and y appear only as part of an expression like this, square root of x squared plus y squared, x squared plus y squared, x squared plus y squared quantity cubed. The point is, if you can write it in terms of square root of x squared plus y squared in any way, then your surface is rotationally symmetric around the z-axis. It's a very powerful geometric conclusion that we get from, again, sort of a casual observation. And there's different ways to see this. One way to see this is that if you look at a point that satisfies your equation, right, whatever the equation is, if you were to rotate it around, now that's a different point. It's got different x's and y's. It's tempting to say, look, if I've got different x's and y's, I'm going to have to plug into the equation, and I'm putting in different numbers. I mean, who knows if it's going to work or if it's not going to work. But having rotated around, that distance is the same for both of these points. And the only way, yeah, sure, there's different x's and y's there, but the only way that x and y are going to show up at all is as part of this expression, which is R, which is where these 2 points agree. Right? So, therefore, if that purple point works, well, then this red point works too. Any rotation of the purple point is going to have the same R and the same Z, and therefore is going to fit into the equation in pretty much exactly the same way. So, therefore, this surface is rotationally symmetric. That's one way to see it. Here's another way to see it, and I like this one too. If you think about the cylindrical equation, and think about thetas, and are there going to be any thetas in this equation? Well, where would theta come from in cylindrical coordinates? The only way thetas could show up is if the x's and y's, you've got r cosine theta, r sine theta. There's some thetas in there. That's where the thetas are going to come from. But if the x's and y's all go into there, then the thetas will all disappear because of the Pythagorean identity, and you will therefore have no thetas. And we've already talked previously about if you have a cylindrical equation that has no thetas in it, then you're talking about something that's rotationally symmetric. Okay, so the reason we care about this is that it is a foot in the door to understanding surfaces and equations. So, for example, let's think about this equation right here. Now, we've seen this equation before, and I made an assertion that it's kind of a bowl-like thing. And you might even kind of believe that because you're like, I kind of see parabolas in there, right? And it seems like it might be sort of parabolic in some way or something. Well, here's the thing. X and Y appear only as part of that special form. So it's rotationally symmetric around the z-axis. Oops, let's try that again. Here we go. So we already know a lot of information. Our thing is rotationally symmetric around the z-axis. Next thing, I can just choose to look in a cross-section. And I don't know, it doesn't really matter. I'm going to look in this cross-section right there. Cross-section where x equals 0. Now, in order to be useful, I'm going to make sure to pick a cross-section that contains the z-axis, which is the axis of rotation, because geometrically I just need that in order to be able to draw the conclusions that I want. Plug in x equals 0, and it becomes pretty easy to see what happens in the equation. The equation becomes just z equals y squared. And z equals y squared, that's an easy one. This is algebra 2. I don't know, algebra 1 maybe? Anyway, this is old algebra, and we, without any question, know what that looks like. That looks like this. That's a parabola. So we know we've got a rotationally symmetric thing. It's rotationally symmetric, and I already understand one of its cross-sections. So I just rotate that cross-section and we win, right? So this actual surface here is going to be what you get when you rotate that cross-section around the z-axis. And now I've got a picture. Everybody see what happened there? I think it's a really nice little technique. Anytime you have something where x and y appear only in that special form. There you go. Side note, this is called a paraboloid. Is everybody happy or just quiet? No questions? Yes?
Does the expression x squared plus y squared have to necessarily be under the square root?
No, because one way to say it is that x squared plus y squared is that square root squared. Right, so in other words, this is written in terms of only the required expression because this is z equals square root of x squared plus y squared squared. And so x and y do indeed, as required, only show up as part of that expression. It's just they show up as part of that expression that I then, of course, do other things to, but that's fine. Yeah. Does that make sense? Okay. Everybody good? Okay. All right. A couple more examples, and I'm going to try to be quick with these. This one's a weirder one. You're going to have a harder time figuring out what this looks like. It kind of looks vaguely. I mean, I sort of see. Is that a parabola I'm seeing, or I see a hyperbola maybe? I think I see circles or something, right? So, but what exactly is going on here? What is this thing? All right, so step one, x and y appear only in the special form. We're rotationally symmetric around the z-axis. Step two, pick a plane that contains the z-axis. Doesn't matter. Just to show off that we can, I'm going to use this plane this time. Doesn't matter. You could have done the YZ plane. Who cares? That plane is y equals 0. And if I plug in y equals 0 into there, my equation becomes that, which again, highly recognizable. And I know Algebra 2 was a long time ago, right? It's easy to get confused as to, wait a minute, which way does it go? Which way does the hyperbola? Is it this way, right? Or is it this way, right? And so you got to think that through. Anyway, make sure you're good with your Algebra 2. Ends up being this one. Again, it's kind of all over, but the geometry, we know that our surface is rotationally symmetric around this blue line. We know what one of the cross sections looks like. So now I just have to think geometrically what happens as I rotate that around the z-axis, again because of the rotational symmetry. And rotating around the z-axis gives us something that looks kind of like that. Again, this we've got a name. This is called a hyperboloid of one sheet. Is that cool? All right. Now there are similar theorems, similar arguments that you can make when you have symmetries around other axes. And I don't want to get rigorous about this, but I think it's a fairly easy appeal to make. That, for example, in this equation, now x and y do not appear in the special form, but y and z do. Right? And so you could imagine then going back up to here and thinking about the argument, and this form is really talking about distance to an axis, and that distance is what's preserved when you rotate around that axis. You can kind of see it working out, and I think it's a good exercise to think that through on your own. But I assert that because y and z in this equation, y and z appear only as part of that special form. This is rotationally symmetric around the x-axis. Try that again. All right, so again, huge information. We've got a rotational symmetry around an axis. Pick any plane you like that contains that axis now. And no particular reason, I'm going to choose the XY plane where z is equal to 0. Again, any plane that contains that whole axis is fine. So z is equal to 0. Well, again, you can kind of plug in, see what happens. You plug in that z equals 0, and our algebra turns into this. Again, we have to flash back to Algebra 2 class and remember, okay, it's a hyperbola. Which way does it go? And you gotta, sort of think it through. And it goes this way, like that. And now again, geometry problem, geometry challenge. What happens when you rotate this purple curve around that green axis? And you just have to visualize it. The result is kind of a hard thing to describe. It's got kind of two. It's tempting to call them kind of paraboloids, right? Because there's a sort of a curved thing that we rotate around, but we didn't rotate parabolas. We rotated hyperbolas, pieces of the hyperbola. So this is, it's like, in my mind, I see two eyeballs staring at each other. So to me, I call this the staring contest. But this is more normally known as a hyperboloid of two sheets. Okay, yes?
Does this always hold true, like if you had x squared plus c squared, would it be?
Yep. Yeah, that's the thing. So there's three versions of this theorem, right? So they're corresponding to rotational symmetries about either of the three axes. Absolutely. Yep. It's a neat trick. And you can make examples for yourself of how to find such surfaces. Yeah. Okay. All right. Okay. Next thing I want to talk about what I call deformations. By the way, the book is not as full as I would like of discussions about these things that I'm talking about now. I think these are neat, important, useful algebraic tricks for doing multivariable calculus. And anyway, I wish the book spent more time on it. Okay, so deformations. The idea here is suppose you have an equation for which you already know what the corresponding surface is. Let's just say. I think this is a nice example because I can look at this and I instantly recognize that this is talking about points whose distance from the origin is 13. So this is pretty clearly a sphere. Okay, what would happen if I do a specific algebraic thing to this equation? And specifically, I'm going to replace everywhere I see a z, I'm going to just kind of erase, and then in its place, I'm going to put 2z. So you'll notice that's what happened here. This z, I'm just replacing it with 2z. So I just tweaked this equation. What did that do to the picture is the question I want to talk. In what way does this tweak of algebra deform the picture, right? If I change the equation a little bit, it's going to change the solution set a little bit. In what way does it change that solution set? So here's the way I like to think this through. Let's think about a point that we know works. This point right here, 3, 4, 12. You can plug that in and this equation works, no problem. The little Pythagorean quadruple is kind of fun. All right, does that work over here in this equation? Well, of course not. I changed the equation. It's a different equation. Why would it work? And you plug it in and see it doesn't work. But we can also kind of think through why it didn't work. Right? When I plug in 3, 4, and 12, most of the equation goes through exactly the same way. The only difference is this 12. I mean, the 12 is supposed to be the thing that gets squared, but it doesn't. It's not the thing that gets squared. This 12 gets multiplied by that 2. We adjusted this equation in such a way that 12 gets multiplied by 2 first. And I'm squaring 24. Everything's all messed up. Everybody see? So you can also get into smart alecky mode and realize that, okay, well, yeah, but look, so the thing, I don't want z to be 12 anymore. I want the thing that used to be z. Right? I want 2z to be 12. And I can make that happen. I can make 2z 12 by just choosing 6 for z instead of 12. Right? I can undo in the z-coordinate what I'm doing to the z-coordinate in the algebra. So this point works. And the net effect, you notice, is that the point that had been at height 12 now is at height 6. This applies to, I think you can see, any point, right? Whatever that z-coordinate is, that z-coordinate is going to get cut in half. And so I claim that this blue algebraic move, replacing every z with 2z, squishes the surface by a factor of 2 in the z direction. Does that make sense? Okay. So roughly speaking, I don't want to overinterpret this, but this is, and let's not get too rigorous about it. Roughly speaking, whatever you do to the variable in the equation, namely replacing every z with a 2z, the coordinates are going to have to sort of undo that, and therefore, in some sense, the opposite is what happens to the surface. Yeah, question?
Oh, for like the squish spheres, does the radius still apply?
Well, radius is this is no longer a sphere, right? Now it's, the x and y directions still have the same radius of 13, that's right. In the z direction, everything's been squished by a factor of 2, so in the z direction, it's just 6.5.
Oh yeah.
Yeah, but it's an ellipsoid, we call it. In the z direction, it's half the radius. Yeah. Okay. So here's another example. And I think this one is also pretty straightforward. Here is an equation we understand. It's clearly a unit sphere, distance to the origin, and all that. Now, what happens when I do these certain things? And in particular, you'll notice everywhere I have an x, I'm replacing that with x divided by a. So I'm going to recognize down here, this is just a casual indication that every x is going to get replaced with, or it's going to turn into the little expression x over a. And same argument, if you think about it, the x coordinates over here are going to have to be a times as big to make up for the fact that you just divided them all by a. And so this stretches that unit sphere by a factor of a in the x direction. And then likewise for the other, so you can see every y, and that's important, got replaced with y over b. And so we're going to stretch by a factor of b in the y direction, and likewise by a factor of c in the z direction. Everybody good? Okay. So notice you get an equation now for what's called an ellipsoid. Yeah. Okay. All right. A couple more. I'm going to let you all think these through. Think about, we already know this is a paraboloid. This is a rotation of a parabola. Well, this thing over here, very importantly, not a rotation. Right? X and Y do not appear in a special form here. They're the A's and the B's, unless A and B are the same. The A and the B here are really messing things up. I cannot just say this is rotationally symmetric. It's not, in general, rotationally symmetric. But what I can say is, but it's just a stretched out version of something that is rotationally symmetric. So we use rotation to understand this, and then we stretch to understand that. Okay, so this is called an elliptical paraboloid. And then likewise, we can take our hyperboloid of 2 sheets, and we can stretch it out, and we get an elliptical hyperboloid of 2 sheets. Okay, so they have a couple of examples in the book, and I encourage you to think these through, draw some pictures, make sure you understand what's going on in these examples. But it's just deforming things that we already understood. Okie dokie. Pausing. Okay. All right, so we finished section 2.1. You'll notice we're not talking about section 2.2. 2.2 is not even on the syllabus. It is good stuff, and I'm sad that we can't cover section 2.2. My inner mathematician thinks that's one of the most important sections in the book. But for the purposes of what we're doing in this class, it's not going to play into how we're going to apply the ideas. And so I'm going to say that sadly we're going to be skipping section 2.2. But again, good news. It's stuff that's not really going to affect y'all as mostly engineers and CS and stat, etc. If you're going to be a math major, then you might want to give it a look at some point. Okay. All right, so we're going to move on to derivatives. And turns out, this is a little bit weird, compared to single variable calculus, where there's pretty much the derivative, and that's it. It's just the one kind of derivative. In multivariable calculus, there's a bunch of them. There's several different. They're all kind of related in a way, and we will eventually we will find that there is a single thing called the derivative that arguably contains all the others in a sense. But in practice, there are different kinds of derivatives in how we actually do business. So that brings up a question. If you have several things going by names that all use the same word, then we have the sort of the philosophical question. Well, what does that word mean anyway? I mean, so what is it? What feature of a construction should we require to call something a kind of a derivative? And so this unifying feature that I call it here, various different kinds of derivatives that we're going to see, they all have this characteristic. They all relate input changes to output changes in different ways. All right, so if you think back to single variable calculus, I think you'll find that the derivative has this feature. The derivative is the thing you multiply by an input change to get the linear estimate of the output change. Right? Okay. All right. So, again, various different kinds of derivatives. We're going to start with one called the partial derivative. Now, this is a personal note I want to insert here. I am going to start with the partial derivatives for various reasons. Let me start with the positive. They're easy to compute. That's a good thing. That's nice. We like partial derivatives for that reason. They are what I'm going to call relatable. They're familiar. They're going to look a lot like single variable derivatives in a way. And that's nice, right? The very first time you see that you make the jump into doing multivariable calculus, it's kind of nice to say, oh, it's kind of like in single variable calculus. That's good familiarity. Also, the book does it this way. And, all else being equal, it reduces confusion if I stay consistent with what the book does. That said, my disclaimers, the downside, ultimately, when you leave this course, I hope that these will not be your cornerstone, fundamental point of view on derivatives. I don't think it's a good choice for that. They have their uses. They're very convenient. They're very powerful in how they allow us certain conveniences. I'll say that. But ultimately, is this what the derivative is? No. This is not what the book is referring to when they say the derivative. It's not what this is. There is a much better, a much more natural, ultimately. It's not as relatable, and it's not as convenient to work with, but it is ultimately better as a perspective of what truly is a derivative. So that's just a warning. So I want you to go into this discussion of partial derivatives, thinking of this as a one tool of many. But don't hang your hat. Don't get too comfortable with partial derivatives, because we're going to take different points of view very soon. Okay, that's a lot of disclaimer. Let me tell you how to compute a partial derivative. We're going to choose to hold all variables constant except for one. Now that seems like are you allowed to do that? Right, I've got a function with a bunch of variables. Can I just pretend that most of them are constants? Well, I mean, I guess, a free country and all that, right? You're allowed to, and you're responsible for the consequences of your actions, of course. If you choose to view those as constants, then you have to admit that what you're going to end up with is really not the same function as what you started with. And so the interpretations we're going to be able to get here are highly limited accordingly, right? But yeah, we are allowed to choose to ignore all but one of the variables. And thus I have, since there is now only one variable that's actually a variable, then indeed we have a single variable function at this point. And if you think about it, if you have a single variable function, you can do single variable calculus. You can take the usual derivative, plain old, regular old derivative of that resulting single variable function. Okay, so that's the process. I'm going to show you some examples in a minute. Real quick, though, I need to show you the notations, how we're going to represent this. A very common notation for partial derivative is what I'm going to call Leibniz-like. It looks like, df dx, sort of. A couple of particulars, though. You have to indicate as the variable which is the one variable that is continuing to be a variable. Which one is the variable for your single variable function that you've created? That's what goes down there. And the other thing is, very importantly, these are not D's. Not a D. We can't let it be D's, because if I say df dx, that's a notation that already exists that means something about a single variable function, and f is just not. F is not a single variable function, right? So I can't treat it like I can't. I can temporarily pretend that it's a single variable function, but I can't assert and claim and therefore treat it as actually a single variable function. So we had to use a different symbol than D. And somebody came up with the idea of this, we call it the partial symbol. And very importantly, not D. Very importantly, not the lowercase Greek letter delta either. And you've got to be careful not to make either of those mistakes. So this is another situation where, ridiculous though it seems, it's a healthy exercise to fill up a piece of paper with partial symbols and, think through how you're going to, what's your little hand mechanics going to be, and how. I like to spiral out. Some people might like to spiral in. I don't know. Take your preference. For me, it just makes more sense to spiral out. I don't know. But think it through how you're gonna make your partial symbols. Okay. Okie dokie. So let's do one. Let's compute this partial derivative right here. And let's see here. Let's prepare for great inconvenience, because look, I've got a product of what you might call three separate factors, one of which is a composition, and there's exponentials and trig and polynomials, and oh my gosh, right? It looks hard. Okay, so we're going to take now a partial derivative of this thing with respect to y. Partial derivative with respect to y. Keep in mind what that means. That means that for the purposes of this partial derivative, x and z are constants. I'm going to treat them like constants because that's what partial derivatives are. Partial derivatives say we're first going to pretend most of these variables are constant. And then we're going to take a single variable derivative after. But so here's the thing. This function, if x and z are constants, that whole factor e to the x, also constant. This whole thing over here, cotangent of blah, 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 also constant. Big, ugly, nasty constant, but it's a constant. Right? Is everybody good so far? Okay. So we've got these constants, and constants are great in derivatives. You just kind of leave them there, right? And so what's actually happening, the actual calculus that's going to happen here is I'm pretty much just going to take a y derivative of y squared, and that's 2y. So the actual taking of a derivative here was very easy, as it turns out. Now, don't forget your constants. Yeah, those come along for the ride. They stay there. And so your answer is all of that. And then, decide for yourself how you want to write that. I think it kind of makes sense, just aesthetically, if only, to bring that 2 out to the front. Just kind of looks better that way. And there you go. There's that y partial. Anybody see how that works? Okay. A couple other examples, real quick. And again, this looks like a hard one. Right? Oh my God. A lot of people would look at this and they see a function to the power of a function and they think, I learned logarithmic differentiation back in high school. And I don't know if they still teach logarithmic differentiation. If they don't, I have a video on it on my YouTube channel, Miscellaneous Topics playlist, and it's literally called Logarithmic Differentiation. Give it a look. It's a cool idea, and it's something I think everyone should know. But anyway, it seems like this ought to be because it's a function to the power of a function. But here's the thing. I'm taking the partial with respect to x, which means everything other than x is a constant. That means that y squared, for example, constant. What I have here is a function of x to the power of a constant. And constants, do the trick where you have to bring the constant down and then you subtract 1. And really the hardest part about this is remembering that you have to use the chain rule here from the point of view of outside-in differentiation. So there you go. No logarithmic differentiation at all. Is that cool? And then likewise, here's another example that we have. Again, it looks like function to the power of a function, but it's not. It's a constant to the power of z. And this is an old news thing. That constant, call it a, for example, and the derivative of a to the z is a to the z times log a. That's just old single variable calculus formula. Everybody happy? Okay. All right. So I personally will nominate partial derivatives as being the easiest derivatives to compute of any kind of derivatives I've ever seen, because it's like single variable derivatives, but I get to just say, constant. I get to treat large parts of my function that I otherwise would have to deal with. I get to just say, I'm just going to treat those as constants. Right? So it's like single variable derivatives, but I get to it feels like cheating in a way, right? So anyway, the easiest to compute that I am aware of. And that's a great thing. Okay. Now, a reasonable concern that you might have in your mind right now is if I write this down and say I'm going to define this thing called partial derivatives, and here's what I'm going to do. I'm going to play make-believe, and I'm going to do what I already knew. Reasonable gripe would be, you're making up nonsense. What does this have to do with anything? Does this look like anything geometrically? Does this relate to anything useful? Or are we just making stuff up? Right? You got to be really careful about this when you make definitions. You're allowed to define whatever you want, but then if you want it to be useful, if you want anyone to care, then you have to show what it means, geometrically or physically or something. Right? It needs to relate to something. So geometrically, what does this look like? I ask. Again, rhetorically. So, Now, first thing I'm going to say, if you want to think about geometry, then you've got to keep track of what kind of a picture are you looking at. Are you looking at a graph? Are you looking at a level set? Is this a parameterization of something? What kind of a picture are we looking at? That's very, very important. So we're going to start off thinking about what this looks like in the context of graphs. So what does a partial derivative look like on a graph? There is a totally separate question, which is, what do partial derivatives look like on level sets? Right? So what does it look like on a graph? Well, keep in mind, here's what a graph is. Right? We're looking at a function from R2 to R1. So x and y are inputs, z is an output. And let's think about what happens when I take a partial derivative here, take a partial derivative with respect to y. Kind of two things happen. The first thing that happens, let's see here. First thing that happens is because y is what I'm taking a derivative with respect to, that remains a variable, but x now gets treated as a constant. And treating x as a constant is something we can literally draw a picture of. Here it is. If I'm at this point and I want to treat x as a constant, that means x is not allowed to change. That means x has to be a. That means that whatever surface I'm looking at, I am literally taking a cross-section where x gets fixed at a. And now a quick geometric appeal, if you fix x to be a certain value, then notice that that is actually a cross-section. You might say it's a cross-section in the y direction because it points parallel to the y-axis. All right, is that cool? Then notice what remains, that cross-section of that surface. That cross-section is also a graph. That gives you height, gives you the value of the function depending on whatever value of y you pick. And taking a derivative with respect to y, we have an existing geometric interpretation. The derivative with respect to y means what's the slope of that tangent line. So there's a very nice sort of succinct then answer to, what is the partial with respect to y? Partial with respect to y, well, it's a slope of a tangent line. Now, of course, to the graph, right? Derivatives are slopes of tangent lines to graphs. But then further detail, we do have to recognize that we only get a curve with which I can talk about taking a tangent line because I fixed x, and namely because I am looking specifically, therefore, in the y direction. So the y partial, slope of the tangent line of the graph in the y direction. Oh, I'm sorry, I lost track of time. I went over there. We'll pick up here next time. And see y'all later. Don't forget office hours in 20 minutes. 13 minutes. Okay. See y'all soon.